Welcome to The Explainer, everyone. I am so pumped to dive into today's topic with you. We're unpacking something absolutely massive, the Titan AI architecture. If you're at all fascinated by the intersection of, hardcore legacy transportation and cutting-edge artificial intelligence, you are 100% in the right place. We're going to look at exactly how this system is designed to modernize passenger rail, essentially transforming a traditional train into an intelligent, data-driven machine. So let's get right to it. Okay, let's ground ourselves in physical reality for a second. Take a look at this beast. This is the Amtrak ALC-42 locomotive. It is a massive, heavy-duty piece of machinery. When we talk about the Titan AI system, it's vital to remember that we aren't just talking about software sitting in some pristine, climate-controlled server room. No, we are talking about equipping this exact, rugged physical environment with an aviation-style AI copilot. It's all about merging raw mechanical power with incredibly sophisticated digital intelligence. So here is our roadmap for today. Number 1, the collaboration layer. 2, inside the locomotive brain. 3, the safety isolation layer. And 4, the 4-phase roadmap. All right, section 1, the collaboration layer, station and train. Right off the bat, it's totally crucial to understand that the Titan architecture isn't just about building a single, isolated smart train. It is about engineering an entirely interconnected ecosystem. Instead of a basic one-way broadcast, we have a dynamic two-way AI collaboration layer operating over a secure VPN, 5G, or LTE. Think of it as a constant conversation. On one end, the station edge AI is sending all this rich contextual data, route info, passenger loading stats, weather updates, and construction alerts. On the other end, the locomotive edge AI is sending back its own real-time telemetry, precise GPS positioning, speed, active AI camera detections, and obstacle warnings. They're constantly exchanging these crucial events. This means the train always knows what's happening at the station, and the station knows exactly what the train is encountering out there on the tracks. Moving right along to section 2, inside the locomotive brain. Now that we've got the big picture, let's actually zoom right into the train itself. Imagine you're stepping into the ALC-42 cab. You are immediately in the engineer's seat. As you can see, it's a spacious but incredibly complex environment. You've got traditional instrument panels, radios, diagnostic screens everywhere. This is the stage for our AI. The goal of the Titan architecture is absolutely not to clutter the space with more confusing dials. The goal is to introduce an AI assistant, named Victoria AI, that actually helps the human operator seamlessly manage all of this complexity. So how does this actually play out? Well, this is where it gets really fascinating. Picture the engineer just talking to the system. Victoria, why are we reducing speed? And the AI responds, vision detected maintenance workers 1.8 kilometers ahead, dispatcher restriction 45 mph, brake curve calculated. I mean, how cool is that? This perfectly demonstrates how Titan takes vast amounts of abstract telemetry data, like camera vision, dispatcher rules, speed calculations, and translates it into a conversational, highly actionable interaction. The engineer isn't hunting through a dozen screens. They are simply having a conversation with their train. Here's another quick scenario, and this one ties right back to that collaboration layer we talked about earlier. The engineer asks, Victoria, how many passengers will board at Chicago? And gets an immediate, precise answer. Approximately 412 passengers, platform 5, boarding estimated 7 minutes. This really highlights how that station-to-locomotive collaboration practically assists the engineer in real time. The locomotive AI has already synced up with the station's passenger prediction systems, delivering those analytics directly to the cab. Now, what's really interesting about this slide is the hardware strategy powering all of this. The architects smartly separate the prototype hardware from the production target to keep costs in check. For the demo and pilot phases, they use the NVIDIA Jetson AGX Orin. It's relatively inexpensive and awesome for easy development. But for the actual production deployment on a shaking, rattling locomotive, they upgrade to the Jetson Industrial or IGX versions. Why? Because these industrial computers give you that essential vibration tolerance, an extended temperature range, and a way longer life cycle, which you absolutely need in a harsh railway environment. But for the AI to actually answer questions about the track ahead, it literally needs eyes. And the Titan AI camera suite, it is robust. We're talking a 5-megapixel global shutter HDR forward camera to see clearly in terrible lighting, alongside 2-megapixel side cameras and a 1080p cab camera. But the real standout here is the optional thermal camera. This is an absolute game changer for detecting living obstacles like people or animals on the tracks at night, or even spotting mechanical failures like smoke or overheated brakes, way before they become catastrophic.
Which brings us to Section 3, the safety isolation layer.
Okay, this right here is arguably the single most critical technical hurdle of the entire project. How do you integrate all of this cutting-edge artificial intelligence with legacy rail infrastructure without compromising the incredibly strict safety standards of passenger rail? To understand their solution, we first need to define CBOS. CBOS is the existing, rigorously certified Siemens train control system that already runs the locomotive. It handles literally all the critical functions. The absolute golden rule of the Titan architecture dictates that CBOS must never be modified directly by the AI. This is foundational. Which naturally leads us to a pretty massive question, one you're probably wondering about right now. In this architecture, can the Victoria AI directly control the train's traction or physically apply the brakes if it sees an obstacle? The answer, a definitive, absolute no. The system is entirely read-only. The AI only observes. No commands are sent to the train's control system whatsoever. So the crucial takeaway here is that Victoria AI is explicitly an advisory co-pilot. By keeping the AI from making physical commands, the architects vastly reduce the safety certification complexity, which aligns perfectly with how advanced systems are introduced in modern aviation. So let's map out exactly how this data flows safely. Step 1, the data originates from the CBOS control system. Step 2, it passes through a read-only gateway, which guarantees one-way traffic. Now, Step 3 is where the magic happens, the Titan telemetry service. Instead of feeding raw data straight to the AI, this service acts as a vital safety buffer. It validates the values, timestamps them, and converts them into structured messages. Only then, in Step 4, does the Victoria AI finally receive the data. The AI can see everything: speed, throttle, brake pressure, GPS, but it literally cannot touch a thing. All right, let's zoom out for Section 4, the four-phase roadmap. So how do you actually take a massive, sci-fi sounding project like this and make it real? Well, you build it progressively. Phase 1 starts off the train, rolling out the smart station with biometric gates, passenger prediction, and advanced ticketing analytics. Phase 2 introduces the AI co-pilot. That's where they install the rugged Jetson computer and cameras on the locomotive in that strict read-only mode we just discussed. Phase 3 enables the networked fleet AI, unlocking that secure collaboration between the smart stations, the locomotives, and the cloud. And finally, Phase 4 looks to the future: assisted autonomy. Subject to strict regulatory approval, of course, this phase would introduce gradual driver assistance features while always keeping the certified human-operated train control system in absolute command. It's a super logical, staged path to the future. And that leaves us with a really fascinating final thought to chew on. As Titan successfully demonstrates how to evolve from a simple smart station platform into a comprehensive, deeply secure AI rail ecosystem, what other legacy safety-critical infrastructures out there are sitting ready for their very own AI copilot? We've just seen how securely layering a read-only AI can completely revolutionize a train. The possibilities for modernizing other traditional systems using this exact architectural blueprint are truly endless. Thank you so much for joining me for this explainer. Keep asking questions and keep learning.